Earth, a unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. This episode explores Everest, the highest mountain on planet Earth. In order to unlock its secrets, a daring mission is undertaken to bring back rocks from the summit. This journey of discovery into the formation of Everest will uncover ancient fossils, hidden crystals, epic weather, and immense structures etched into the mountains. All part of the incredible story of how the Earth was made. The Himalayas stretch 1,500 miles across Asia. They're home to 14 of the tallest mountains on the planet. And one rises above all others: Everest. At 5.5 miles tall, Everest is the highest mountain in the world. In order to figure out how this giant mountain was made, geologists need evidence. Rock samples from Everest. It's a dangerous mission, and only a few people are willing to undertake it. Kenton Kuhl is one of the world's best high-altitude climbers, and he will embark on this geological mission to the summit of Everest. His instructions from geologists are to collect rock samples from 3 places: 1 from the summit and 2 from lower down. These incredibly rare samples will give investigators crucial evidence. Kenton is at Everest Base Camp. Pitched on jagged rocks at 17,500 feet, this camp is over 3 miles above sea level.
Sorting out the last of the items I need to take on a summit push. And I've just been to collect a load of Ziploc bags, which I hope to put all the samples in.
Over the next 5 days, he will climb 12,000 feet, the equivalent vertical height of 8 Empire State Buildings. Kenton starts his mission from base camp. He negotiates the Khumbu Icefall, a frozen river with crevasses thousands of feet deep. It's a treacherous ascent, as all this glacial ice is constantly moving, and looming ice towers threaten to collapse. Kenton now has the most dangerous section ahead of him. At 21,000 feet, he is already higher than Mount McKinley. He has a sheer ice climb up the side of Everest. Winds reach speeds in excess of 100 miles an hour, and temperatures drop to -40 degrees. Since leaving base camp, Kenton has climbed for 4 days. At 26,000 feet, he reaches the point which joins Everest and its neighboring mountain, Lhotse.
So here we are, this is the South Col, one of the highest camps in the world. 7,950 meters. So high that nothing can actually live here.
From this camp, Kenton will leave at 3 a.m., climb through the night, and aim to arrive at the summit in the morning.
It's pitch black. That's 3 in the morning.
Timing is crucial, and the weather must be ideal. The window for ascent is narrow. There are only around 12 days of the year when climbers can make it to the summit. Kenton must take this opportunity. He now ventures into what climbers call the death zone. Oxygen is needed to make the climb, as the air is 3 times thinner than at sea level. 1 in 10 people die climbing Everest. And most fatalities occur during this final stage.
One more.
Kenton finally reaches the top of Everest.
8,850 meters. We are the highest people in the world.
This is the view from the highest place on planet Earth. For most climbers, the summit is the ultimate goal. But for Kenton, his mission has only just begun. He heads just below the summit to find an exposed outcrop of rock. Kenton's first sample is a gray limestone. It's soft and easy to break off. This is a sample of the highest rock in the world. 1 down, 2 to go. Kenton descends further to collect the next sample. Just below the summit, the rock changes. Climbers call it the yellow band due to its distinctive color. The rock is dramatically different from the summit. Much harder and yellow in color. This is a layer of marble.
All right, there we go. This is off the yellow band. All right, so that's that. That's the yellow band. We've collected samples from here. It's not been very easy. We're getting out of here. It's beginning to snow.
But he has one more to go. Kenton starts the long descent to where he'll get the next piece of evidence. He enters into the Western Cwm, a huge U-shaped valley which has been carved by the Khumbu Glacier, a frozen river of ice that has relentlessly pushed downward over the past million years. Rock and debris in the glacier have ground away at the rock underneath, revealing the base of Everest. Kenton needs to take his final sample from this area of distinctive white rock. Granite.
So here we are in the Western Cwm on Everest, about 6,400 meters. I'm actually stood underneath one of the easier outcrops to get to. This is a big sort of granite cliff above me.
This white rock is full of crystals. It's extremely hard and different again from the summit limestone and the marble.
Yeah, we've got quite a nice sample of the granite there.
With the 3 precious samples safely packed away, Kenton takes them to the University of Oxford. Here they will be analyzed by the world's leading authority on Everest, Mike Searle.
So Mike, this is your summit rock. Now, that is from the top of the world.
Well, this sample, Kenton, is probably one of the most important samples of the whole expedition, so it's literally worth its weight in gold geologically. This came from the summit of Everest right there. The next rock down that you collected was from the yellow band. And even further down is another rock, a granite.
Almost a complete picture of Everest.
That's right, yes.
Fantastic.
Yeah.
These 3 rocks are the major components which make up Everest.
All that effort to get up to the summit was, I can tell you, was absolutely worth it to get this sample.
Good. I hope so.
So the next step is we want to find out what's in it.
The summit rock is cut into a thin section. So thin, light can pass through it.
Okay, let's have a look at this slide of a limestone that's from the summit of Everest.
The highest rock sample in the world reveals its secret.
Oh, that looks interesting. What's that? We've got a section here through a crinoid stem. A crinoid is a sea lily.
From fossil records, the section can be dated. It is over 400 million years old. The sea lily is evidence that the summit rock of Everest was formed in an ancient marine environment.
So from seeing this evidence, we can categorically say that this rock would have started life at the bottom of the sea floor. And then I've collected it from the very, very top of the world, from the summit of Everest itself. That's just amazing.
But a mystery is revealed. How had rock with marine fossils in it ended up on the top of Everest? The mission to collect rock samples from Everest has uncovered 2 clues as to how it formed. Samples show that the mountain is made from 3 distinctive types of rock. Rock from the summit of Everest contains marine fossils, proving it started life on the bottom of the sea. To figure out how seafloor came to be on top of the highest mountain in the world, geologists need to find evidence that is millions of years old, going back way before the Himalayas were even formed. 400 million years ago, no trace of the Himalayas existed. The sea lily, now fossilized on the summit of Everest, is proof that there was once water where now this great mountain stands. But to figure out whether this was just a shallow inland sea or a great ocean, geologist Mike Searle travels to the Himalayas. He begins the investigation at the Garkola River. It flows down from the high Himalayas and carries with it an intriguing clue.
The rock I've got in my hand at the moment may look a bit boring and insignificant. It's just a pebble taken from the river, but it's actually a key clue as to the formation of the Himalayas and the evolution of the rocks. It's almost by magic, but when you smash a rock like this open, what it reveals inside is an absolutely beautiful fossil. And this fossil is what we call an ammonite.
This ancient creature is part of the squid family. It's proof of a complex ecosystem found in a deep ocean.
Giant squids swimming around in the seas that once lay between India and Asia, and this is some of the key evidence that we've got, that there was a major ocean between the continents.
But to find marine fossils in the high Himalayas and on the summit of Everest, some immense geological force must have pushed the ocean floor upwards, above the water. Figuring out how this happened has taken geologists over 100 years. The first lead in this investigation came from an unlikely place: Antarctica. In 1910, the renowned Antarctic explorer Robert Scott began his ill-fated expedition to the South Pole. After reaching the pole, Scott and 5 of his team died. When the bodies were discovered, among their equipment were carefully wrapped and labeled fossils. The fossils were part of an ancient plant called Glossopteris, and specimens are preserved at the British Antarctic Survey.
Glossopteris is a type of plant known as seed fern, and from many different lines of evidence, such as roots and leaves and preserved trunks, paleontologists think that Glossopteris is actually a type of tree.
Soon, this humble tree fossil was found across the globe. In India, South America, Africa, Madagascar, and Australia. Geologists now had a puzzle. How had this one species of plant spread between continents, separated by thousands of miles of ocean?
Glossopteris is a very important fossil because it could not have dispersed over vast distances. It couldn't have just been dispersed by the wind or by birds across oceans.
If Glossopteris couldn't cross oceans, then scientists were left with one conclusion. When these trees were alive, 250 million years ago, the continents were all joined together. They were part of a supercontinent geologists call Gondwana land. Glossopteris was able to spread across this ancient landmass. But then, Gondwana was split up by violent tectonic forces, which pushed the continents apart. And 80 million years ago, India broke away from the supercontinent. It traveled north and eventually smashed into Asia. To get the full picture, geologists now knew they must get an exact date for this collision. Once again, they turned to marine fossils.
We know the age of collision of India and Asia from several factors, but the most important one is the age of the youngest marine fossils that are preserved along that collision belt. And the age of those fossils is very precisely dated, 50.5 million years.
80 million years ago, India left Gondwana. 50.5 million years ago, it hit Asia. India traveled 4,000 miles in just 30 million years. Very fast in geological time.
India was drifting northwards across the Indian Ocean at very rapid plate tectonic speeds, and we're talking here between 10 and 12 inches per year, which is very rapid.
It's this speed that goes some way to explain the unique size of the Himalayas. Because, as with any smash, the faster the collision, the bigger the wreck. The investigation has now uncovered clues to prove India and Asia were once separate. Ammonites are evidence that an ocean once existed between India and Asia. Glossopteris fossils prove that India was once part of a supercontinent called Gondwana land. The next part of the investigation is to discover how this intercontinental smash gave rise to the tallest mountain in the world. Geologists piecing together the story of how Everest was made have shown that 400 million years ago, a wide ocean existed where the Himalayas now stand. India was part of Gondwana land until 80 million years ago, when violent tectonic forces threw the planet into turmoil and split up this ancient landmass, pushing India northwards. 50 million years ago, India collided with Asia. And for the next 30 million years, this intercontinental smash began to shape the world's highest mountains. Traces of the first stage in this process can still be seen in the Himalayas today. The best way to spot them is from the air.
Because the high Himalayas are so incredibly inaccessible, I mean, just look at that view out there. There's a sea of mountains, all of them are over 20,000 feet. There must be hundreds of them. And those are impossible mountains for a mere mortal to climb.
This is geology on a massive scale. The distinctive formations come into view. Huge folds of rock, clearly seen on the sides of the mountains.
All of these folds that we're seeing right here on Dhaulagiri and Tukche Peak were formed during the first part of the Himalayan mountain building process. So when India first collided with Asia, the first thing to happen was that the northern margin of India started buckling and folding. And those folds are just so spectacular. When you look out the window here, they're just unbelievably impressive.
Like a giant train wreck, India collided with Asia. The land and ocean floor that lay between literally folded up under the enormous pressure. But folds are only part of the story. Alone, they don't explain the Himalayas' vast size. Back on the trail, Searle is on the hunt for further clues.
This is what makes the whole trip really worthwhile. We've just spent 5 days hiking up through the jungle, through the forest, pouring with rain, and up there, finally, are the high Himalayas. I just love those mountains. Look at those peaks up there. They are absolutely beautiful.
Searle points to an intriguing giant scar which is revealed on the face of one of the mountains. It's evidence of the next dramatic phase in the building of the Himalayas.
This is a sketch of what we're actually seeing in front of us, with the big mountain of Dholagiri here and the big folds on the peak of Tukche to the right, with this enormous great fault that is magnificently exposed right along the base of Dholagiri, coming right down to the Kaligandaki river valley at the bottom.
The fault is a fracture running right through the mountains.
Well, the first step in deforming the Himalayas is that the rocks are folded into giant folds. And when that process continues, the rock can no longer fold, so they become overturned folds. And when the process continues even further, that overturned fold actually moves along a very discrete fault plane. And that's exactly what we see throughout the whole Himalayas. So rocks are formed by folding and thrusting.
Rocks can only be bent so far. Once rock has been bent beyond its limits, it breaks and causes a fault. The process of faulting puts different rock types one on top of the other.
Faults are juxtaposed rocks of two different types. So the big, huge fault that cuts through the tops of the high Himalayas, the top of Everest, are rocks that are putting limestones over marble.
This is exactly what was revealed by Kenton's rock samples from Everest. Limestones at the summit, lying on top of the hard marble of the yellow band. Evidence that the top of Everest was initially created by folding and faulting. But this only explains part of the story. To create a mountain the size of Everest, geologists knew that there must have been another, more powerful mountain-building process at work. Clues to exactly what this process was can be found in the Kalemdikola River.
This river is a giant garbage chute, bringing all these boulders eroded off the high Himalayas to the north and sweeping them down in great floods down to the plains of India to the south. So this was a great place to come to sample all the rocks that make up the high mountains to the north.
As any detective knows, some of the best finds are made by sifting through garbage. This time it's garbage from the Himalayan peaks.
This is exactly the rock I've been looking for. This is a beautiful example of a kyanite gneiss, which is composed of these beautiful blue bladed crystals of kyanite.
Kyanite is a gemstone, and it gives a clue as to how these rocks formed.
This mineral is very specific to a geologist, and it tells us that this rock has been buried to depths of about 30 miles or more under high temperature and high pressure.
Rock was not only pushed upwards by the collision, but also down towards the Earth's molten core. Heat and pressure changed the rock and formed kyanite crystals. Another boulder in the river gives a further clue as to what was going on at these great depths.
This white rock is a Himalayan granite, and most of the highest peaks of the Himalayas are actually formed of this rock. And of course, the base of Everest is formed of exactly the same. The presence of these white streaks tell me that this rock was actually partially molten at the highest temperatures during the Himalayan mountain building process.
The rock was pushed so far beneath the Earth's surface that it reached heat in excess of 4,000 degrees Fahrenheit and began to melt. Once it was molten, it was able to move and flow.
Well, you can think of the Himalayas more as a conveyor belt system, taking Indian plate rocks, pushing them down deep in the crust. They are altered by heating and increasing pressure, eventually melting to produce granite, and then forced back up to the surface along these giant shear plains.
20 million years ago, this amazing conveyor belt system was at work. As India pushed northwards, a liquid band of buoyant rock was forced towards the surface and cooled, forming a solid layer of granite. A process called channel flow.
Granite's a very buoyant rock, so when they're formed by partial melting of the crust, normally they're pushed up through the crust to form mountain ranges like you see in the Sierra Nevada or Yosemite National Park, for example. The Himalayas are different. These granites are flowing almost horizontally from where they formed, the southern part of the Tibetan Plateau, to form the high peaks of the Himalayas. And it's this conveyor belt system that keeps the high Himalayas actively uplifting to this day.
The mountains were repeatedly jacked up to epic proportions. It's this unique process which accounts for the Himalayas' immense size. Kenton Kuhl's mission to Everest uncovered an unusually thick band of granite. Proof that Everest's awesome size is due to the process of channel flow. Geologists investigating how Everest was built have discovered folds and faults, proof of the initial mountain building process. White stripes of granite indicate the rock was melted at over 4,000 degrees, forming a giant conveyor belt of mountain building power. But the Himalayas were set to become part of a geological battle between catastrophic forces and powers which would challenge the very height of Everest. 400 million years ago, the Himalayas started out life at the bottom of an immense ocean. 50 million years ago, they were thrust into the skies as India smashed into the Asian landmass. Since that time, tectonic forces have created the tallest mountain in the world. But what of the immediate future? Will Everest continue to rise, or will this giant soon be cut down? John Galetska is investigating whether the processes which built Everest continue to this day. He has traveled to the remotest regions of Nepal and India, setting up GPS stations, which he hopes will provide him with the answer.
All right, come as far as I can by car, and I've got a 3-hour walk straight up the slope. Namaskar.
Just like a GPS in a car, this station is able to pick up signals from satellites and monitor any movement of the ground.
The GPS station has been operating continuously for the last 5 years, so every second of every day of every month of every year, it's taking a data sample, and what it's looking for is changes in the position of where this station is, but how it's moving, the velocity of this station, believe it or not, and even changes in velocity.
The readings from the GPS show that India is still moving, about 2 inches every year. 50 million years after its initial collision, it is still on its relentless journey northwards, pushing underneath Asia. And as it does so, Everest continues to be pushed higher. But there is a dark consequence to this mountain building. Earthquakes.
So what's going on here in the Nepal Himalaya, we've got the Indian tectonic plates sort of ramming into Asia. In this case, India is losing out. It's being forced under Asia. But it's unfortunate that they're locked frictionally, and eventually, over the course of hundreds of years, that strain is accumulated and then released suddenly in a giant earthquake.
The Himalayas have seen 15 major earthquakes in the past 100 years. The most recent to hit was in Pakistan, October 8, 2005. The quake devastated the region. Galetska's readings show that another earthquake is on its way. Kathmandu, the capital of Nepal, lies in the center of the danger zone.
When that earthquake happens, not if, when that earthquake happens, it's going to be several minutes of terror. There'll be strong shaking, you know, in Kathmandu. There'll be just collapsed structures. You'll see landslides on all these mountains. It's going to be complete devastation. 26 million people in Nepal, 50 million people along the whole arc of the Himalayan range. All of these people will be affected.
These devastating earthquakes are the result of a very active mountain belt. Further evidence that Everest is being actively pushed upward. But there is a second force at work in these mountains: erosion.
There's a constant battle going on in nature here between the uplift of the Himalayas and the down-cutting of erosion.
Erosion in the Himalayas is ferocious. A clue as to the reason why lies in a small village 300 miles east of Everest, Cherrapunji. It's the wettest place on planet Earth, averaging over 432 inches of rain each year. This place is 12 times wetter than Seattle. And the reason for all this rain? The monsoon.
The Indian monsoon system is an almost unique system on the planet. And the ultimate driving force is the high mountains and the high Himalayas and the Tibetan Plateau, which is by far the largest area of high elevation on the planet today. And that causes this massive high pressure system during the summer months, which results in the sucking in of all the warm, moist air from the Indian Ocean.
This seasonal weather system blows in across India. Clouds build and rise as they hit the high mountains and form heavy rains which fall across India. Those rains reach their maximum on the southern slopes of the Himalayas.
During the height of the summer monsoons, some of these rivers are able to rise by 20 or 30 feet in one storm. So where I'm standing now, the levels of the river will be way up over here.
Each year, 264 cubic miles of fresh water, enough to fill Hoover Dam's Lake Mead 30 times over, pours down the slopes of the mountains. This water feeds some of the largest rivers in the world: the Ganges, the Indus, the Irrawaddy, and the Yangtze. The Himalayas are the water tower of Asia, supplying fresh water to a fifth of the world's population. But all this water is having a dramatic effect on the mountains. Fast-flowing rivers cut steep-sided valleys. High in the mountains, rain turns to snow, feeding glaciers which carve into the upper slopes. All these forces are at work today, wearing away at the Himalayan peaks. Because the monsoon is so powerful, geologists suspect that Everest and the Himalayas are being worn away perhaps more quickly than any other mountain belt in the world. Since 2004, a powerful new technique has emerged that can actually measure how fast a mountain is being worn away. It uses high-energy particles from space.
At present, we're all being bombarded by cosmic rays. They come from distant parts of the galaxy.
When these particles hit a rock surface, a chemical change happens. It's like a kind of cosmic sunburn. Erosion from rivers and glaciers expose rock surfaces to these cosmic rays. And just like sunburn, the longer the rock is exposed, the greater the damage to its surface. By measuring the amount of cosmic sunburn in the rocks, geologists can figure out how quickly rivers and glaciers are cutting into the mountains. But working this out needs very precise science.
The concentrations that we're trying to measure are so small they're equivalent to putting a pinch of salt in an Olympic-sized swimming pool and measuring 1 or 2 grains of that salt.
After years of research, Owen has discovered the maximum speed of erosion. 1.1 inches per year. That's 6 times faster than the Rocky Mountains and faster than anywhere else on the planet.
All mountains suffer from erosion. They're built up by tectonic forces and erosion wipes them down again. The Alps, the Rocky Mountains, the Andes all have erosional potential, but nowhere has such huge erosional potential as the Himalayas. The erosion here is far greater than anywhere else, and the main reason for that is the summer monsoon.
The battle in nature between uplift and erosion continues. But the question remains, which one is winning? Is Everest shrinking or growing? In 1999, a team of geologists set out to answer this question. They placed a small GPS station near to the summit of Everest. After 2 years of monitoring, the team had their answer. Everest was, in fact, still growing. 1/4 of an inch every year. The world's tallest mountain is still getting taller. The investigation into the growth and movement of the Himalayas has revealed the following evidence. GPS data shows a very active mountain belt that is still uplifting. Cosmic ray dating proves that the Himalayas are being eroded faster than any place else on Earth. Geologists now have the tools to predict Everest's future. It and the Himalayan mountain chain will continue to rise. Aided by new technology, discoveries are still being made in the Himalayas. And recently, one reveals that the rise of these mountains was so immense that it might have changed the very course of Earth's history and plunged the entire planet into a deep freeze. Everest, 50 million years in the making. Today, the Himalayas stand as the biggest, highest, and most active mountain range on the planet. They are mountains of superlatives. The deepest valley, falling over 20,000 vertical feet. The highest plateau, the longest sheer rock face. Hundreds of peaks, higher than anywhere else on Earth, and many have never even been named. The formation of the Himalayas has changed the entire landscape, an epic evolution from ocean to immense mountain range, and created one of the world's most important weather systems, the monsoon, which supplies fresh water to 1/5 of the world's population.
The Himalayas in Tibet are a really exciting place to work for a geologist. This is because it's such an active and dynamic environment. Not only that, it's a very important area climatically.
Scientists investigating the Himalayas have uncovered some surprising results. Discoveries which would suggest that the rise of the Himalayas might have had an impact on the climate of the entire planet. The discovery came about almost by accident, while scientists were studying a process called chemical weathering. Every time it rains, carbon dioxide in the atmosphere dissolves to form acid rain. When the rain falls, it eats away at rock surfaces. This weathering process takes CO2 out of the atmosphere and locks it away in the rocks.
If that rock is interacting with the atmosphere, it pulls down carbon dioxide, and that leads to a negative greenhouse effect, if you like, an icehouse effect. So you get more weathering, you pull down that carbon dioxide out of the atmosphere, and that leads to cooling.
The more CO2 there is in the atmosphere, the warmer the global temperatures. Take CO2 out of the atmosphere, and temperatures are reduced. Then, scientists discovered a major coincidence. The dramatic rise of the Himalayas over the past 20 million years coincided with the gradual fall of global temperatures, which led to the start of the last major ice age. The pieces of the puzzle fell into place. As the Himalayas uplifted, they had acted like an ever-growing giant sponge and absorbed massive amounts of CO2 from the atmosphere.
The uplift of the Himalayas and Tibet lead into the drawdown of carbon dioxide from the atmosphere by these weathering processes was probably one of the major factors in lead into the cooling that culminated in the ice age that started about 2.5 million years before present.
A cooling effect which was so intense that 2.5 million years ago, it contributed to a global deep freeze. An ice age that affected the entire planet and had a dramatic impact on all life on Earth. And geologists are sure that the Himalayas will continue to exert an immense influence on our planet, as these mountains are still growing. As India pushes northwards under Asia, the building cycle continues. More mountains will form. Over the next 10 million years, 300 miles of land will be forced under Asia. The entire range will grow even taller. Out in this vast wilderness of icy peaks, geologists are still making discoveries.
For geologists, it's exciting in terms of the science because you get to areas where few geologists have been before.
As the research continues at Everest and across the Himalayas, it is a wonder what secrets they might tell us in the future. The evidence for Everest's incredible geological journey has been revealed. Ammonites, evidence that an ocean once existed between India and Asia and that the continents collided 50.5 million years ago. Folds and faults, proof of the initial mountain building process. Granite, evidence of a giant conveyor belt of mountain building power which pushed Everest to its immense height. GPS data reveals that the Himalayas are the most active mountain range on the planet, and Everest is still growing. Everest today stands as the highest place on planet Earth. But in millions of years to come, there will perhaps be another mountain big enough to challenge this giant, living proof that the Earth is never at rest.